So let's go ahead and just start off with your background. Maybe just tell us a little bit about you.
Sure. My name is Jack. I'm a PhD student at Cornell at the New York City campus, Cornell Tech, and I'm a part-time researcher at Meta. I'm planning to graduate in a month or two. I've been in the AI language model world for doing research for around 7 years, which has been quite a journey. I feel like things have changed every single year. I got started as an undergrad at a small lab at my school, and then I did the Google Brain residency around 2020 to 2021, and then started at Cornell in 2021. And yeah, I guess it's been this is my fifth year now.
hmm Awesome. So yes, maybe tell us a little bit about how you first got interested in computer science.
In computer science, um, sure. I think it starts by being interested in computers, which is something that was definitely true from a young age. I think the first thing I ever did that really resembled computer science was programming on a calculator, like a TI-84. And then I was lucky I went to a high school that had a really extensive computer science program. So I took like tons of different classes as a high schooler, like parallel computing. They actually had a couple different artificial intelligence classes. And I did a lot of coding then, just like in my free time. Like, I think I was working on Minecraft mods, like writing them from scratch. And then I guess in college, I was like really deep into the software engineering journey. I was in the summers working at this startup in Washington, D.C. that was like really small and trying to build a consumer app. It was kind of like Slack, like a more sophisticated Slack. And so I think I just put in tons of hours. Like they didn't really have very many senior engineers, so I had a lot of
hmm
responsibility and got to write like a ton of code. Um, and then I did a couple actually internships at Google, also doing software engineering. And I think I liked it a lot, but I always had this sense that I wanted to do something a little more creative.
hmm
And then by a roundabout way, I tried to build. So when I was 21, I got diagnosed with this kind of like weird case of thyroid cancer, and I was sick for about a year. And I during that time was like obsessively reading these studies that come out in a couple different places. And I think I tried to build this automated summarizer that would like the idea is it would sort of pull in the latest clinical research that's available from like the US government and then summarize things and kind of aggregate them and filter for what might be relevant to you. That was the goal. And so I think that's the first time I used text embeddings and like tried to do classification. And I thought it would kind of work. Like I think even in that time, was that 2017? I or 20 around then, or 2018, I had this sense that like the AI was really good and should be able to solve these problems. And the summarization was horrible. Like, I don't know, LSTM based
hmm
kind of specific clinical summarization modules. But that kind of got me interested in why. I think I implemented some of my own sentence embedding models at that time. And I was like, this is really cool. Like the idea of word vectors is kind of amazing, even to this day. And yeah, that set me on the research path, I think, from there.
hmm Awesome. So I guess like you mentioned that like now you're at Cornell. Maybe tell us a little bit about your time during undergrad and what motivated the decision to get a PhD.
Well, I think I was interested in research. Like I
hmm
kind of mentioned, I was looking to do something a little bit uh just something less. I think to me the software engineering work felt a bit like construction, where it's like you have this blueprint of what you want to do and you spend all day kind of like hammering away or sawing things. But I don't know. I guess research just seemed a lot more abstract and creative to me, and that was really appealing. So I was looking for a research job, and then I actually did this other research job that was like more like in networking when I was early in college. I was like, oh, this is okay. It wasn't the best project for me, maybe not the right area. And then after I was sick and then was out of school for a bit and then came back, I found out about this professor that does or was working on like clinical text processing, essentially like NLP and with a biomedical focus. I was like, this is perfect. And I kind of talked to her, and she ended up giving me a research position. And at the beginning, you kind of get guided towards what to work on. It's not till later that you start to pick your own projects. So she kind of set me up with something, and eventually that turned into like a Python package for doing essentially jailbreaks on the models of the time. Um, and yeah, I think it turned out really well. It was really fun. It was really like invigorating, honestly. Like finding these things. It's kind of like detective work, like figuring
Mm-hmm.
out what everyone else is doing and where the holes are, what doesn't make sense, and where we can contribute. And there were sort of like a lot of ups and downs, I think, which can be draining, but also like really exciting. And I definitely felt like I was in the right place career wise after that. Like this is the right
Mm-hmm.
job for me.
Mm-hmm. Tell us a little bit about your time as an AI resident at Google right after undergrad.
Right. So that was right when the pandemic started.
Mm-hmm.
And so it was fully remote. Um, yeah, it's a really interesting program. They give you a tremendous amount of flexibility. I think the beginning was kind of like an education of sorts where different people from Google would tell you about like what they worked on and teach you things. And then there's this project matching phase. And I was debating between working on dialogue, which in retrospect might have been also really interesting. But then I ended up working on vision with some vision researchers. Like we were working on self-supervised learning on the pixel level. So like you kind of warp an image and then you can learn by trying to undo the warp or something like that with different warps and different kind of like learning algorithms. And that was pretty cool. Honestly, like we didn't publish on it. Our main highlight was something internal, which is that we achieved the highest score on. So Google has all these internal benchmarks, and we got the highest score on like a pet face feature detector benchmark.
Mm-hmm.
So we had like the best model for locating like the nose of a dog in an image. And so then we actually had to spend some time like kind of integrating that. I think at one point it was running in the Google Home or something like that. Um, and yeah, I mean Google's great. The infra there is insane. It's unlike anything I've ever seen. I mean, there's a learning curve, but just the way that they distribute and allocate compute is so sophisticated. Like it's so impressive. I'm sure it's only grown since then. And the people there are so smart. It's a great place to work, honestly.
Mm-hmm. Awesome. So, after your time at Google, you chose to come to Cornell, and I think you're advised by Sasha Rush, who's obviously incredible. Maybe just tell us a little bit about, why you chose Sasha, that process of first, joining his lab, and some of your key points throughout that journey.
Sure. Yeah, Sasha's the man. He's a great guy. How did I choose Sasha? I knew one paper that they worked on called Neural Linguistic Steganography, which is a paper about embedding codes in natural text and decoding them using like GPT-2 models. And it's
Mm-hmm.
so cool. And I was like, this is awesome. And then I saw him like in the pandemic era live streaming himself learning Triton. And I watched that for a while. I was like, this guy's the man. Like, this guy's great.
Mm-hmm.
And then I think, yeah, I applied, maybe emailed him. And then, you have interviews with different places. And I
Mm-hmm.
talked to him for a while about this kind of adversarial stuff. I was thinking about, like, how do you build models that are
Mm-hmm.
robust to many different changes and small changes in the input, like on the text level. And we had
Mm-hmm.
this like great conversation. And then Yeah, I got admitted to Cornell. The way they do it, at least for me, is that you kind of get admitted directly to your advisor. And so they
Mm-hmm.
do have this optional rotation thing you can do, but I didn't do the rotation. I just sort of started working with Sasha right off the bat.
Mm-hmm. Cool. And I guess like throughout your PhD journey, were there any like key moments, key things you learned?
During the PhD,
Yeah.
yeah, there's a lot. I mean, you get so much. I don't know if I'd say you get smarter exactly, but like so much more effective, like better at teaching yourself concepts, better at managing your time, better at picking problems, better at maximizing the impact you can have based on like what your own skill set is. I mean, it's such a valuable experience. I think the main takeaway for me is the process, like kind of once you pick a problem to work on and you believe like from first principles, like it's kind of like you have this opinion about the world, like this is what I think is true but no one is doing, or this is how I think something really works, and then there's this quest to like demonstrate it, like coming up with an idea, testing it for a long time, learning something, like maybe this idea wasn't actually a good idea for X, Y, and Z, or maybe we have to build a whole new infra suite to like kind of accommodate this, or maybe we have to completely change the existing evaluation so it can do this like testing, and like it's just a really long road to actually get to something that works. And I think once you go through that a few times, you kind of get used to that, like weathering the ups and downs and kind of persevering even when things don't go your way. But I think that took me a long time. Like I remember in the beginning of my PhD just being so emotionally invested in every outcome and like
Mm-hmm.
opinionated about like how things should work in the end.
Mm-hmm.
And over time, I think you get less um, emotional and less opinionated.
Mm-hmm.
And yeah, that's like kind of the quest of the scientist, you know. And I know you can do that in industry, but I don't think there's any learning process that would have been like nearly as efficient as the one that I went through.
Mm-hmm. Okay, cool. I guess like let's maybe dig a little bit more into your research. So, you say you're interested in representation vectors within language models, mostly called embeddings these days. And then specifically you're interested in like where they come from, what they mean. I mean, you're really trying to like understand and improve these vectors. Maybe just tell us a little bit about like how you've sort of have gone through, really understanding these representation vectors, any like maybe sub areas that you want to discuss.
Yeah, I think that's true. I think my kind of current research focuses are a little broader than that,
Mm-hmm.
but I still believe that. Like, if you run a model, like a language model, a neural language model, and look at the inner representations, they just look like random floating point numbers. Like they have no interpretation to humans, and yet they should be, they clearly mean something in some way, because like the model is able to use them to generate good predictions, and like the models are so good, like you talk to ChatGPT, it feels like you're talking to a person, but you look under the hood and it's really just kind of multiplying and adding these numbers that have no meaning to you, and I think that's like really compelling. And so yeah, I can highlight two things we worked on in that direction. One was about trying to take embeddings or activation vectors from the middle or the end of models and predict the text that went into the model. So the question is like, how lossy is the computation that's happening in a language model? Like, is it losing information about what it started thinking about, or is it kind of preserving it? And how does this change based on how long the input is and how big the model is? And it's a really hard problem, like for various reasons. Like if you have this one vector that comes out of the end of a model, the the problem of trying to regenerate the text that went into the model, if the vector is like pooled, and if it's the very output of a deep neural network, is actually very hard, because like really similar text will generate almost the exact same vector. So like disambiguating them like learning to disambiguate them, it is really challenging. And we ended up doing it really well. And like I mentioned, the process, like, so, I was working on this thing for months. Like, I had a system that could take an embedding and generate text, but it was pretty bad. Like, we had this metric that said, okay, the text is about like 35% similar to the original text. Like, random is zero, so we're beating random, but it's pretty bad. Like, we think this process isn't actually lossy, so we should be able to get to 100. And if we can't get it to 100, we should be able to get to 80 or something. But I was stuck at 30. I got it to 35. I was working on this for months and months and months. We tried so many different things, and the approach that ended up working was this. It's kind of like a diffusion model, like an iterative guessing, like what's the activate or what's the embedding, what's the text that's in the embedding, check the embedding and like kind of guess over and over and get closer over time. And then we got that number up to 90, and I was like, this is great. Like, just after working on something for so long, and you kind of believe it should be possible, but you're not really sure what approach should you use. And in retrospect, I think what we ended up using makes sense, but just going through that struggle, I think, was really valuable for me. And the outcome's pretty cool. So, like, if you generate embeddings from a bunch of documents, you can basically assume that a motivated adversary can, like, perfectly or almost perfectly recover the text that corresponds to the embeddings.
Mm-hmm. Awesome. And you've also worked on several different projects. Like for instance, like you proposed the first exact measurement of language model capacity in estimated GPT models to memorize 3.6 or so bits per parameter. You worked on this text embedding model and you designed a new training algorithm for it, where you're sort of incorporating context at test time. Maybe just tell us a little bit about some of the projects you're proud of.
Yeah, sure. Yeah, I mentioned the contextual embedding model and some of the embedding text recovery work, which we call inversion. Like, if the language model is a function or the neural network is a function, we're trying to learn the inverse. I also worked on this study of memorization in models. So, like, I guess you can think of this to make an analogy from the embedding stuff. And instead of trying to figure out what the text is that's encoded into an embedding, we're trying to figure out what text is encoded into the parameters of a trained model.
Mm-hmm.
And I think the easiest result to explain is when you do that with uniform data, like if you kind of if you have a distribution from which you can compute the entropy of samples. So like in a uniform distribution, or like, what is it, Bernoulli, whatever, like whatever distribution is just zeros and ones a certain number of times with
Mm-hmm.
50% probability. um if you have this string like 0, 0, 1, 1, 0, 1, that's 6 bits. So we did something like that. Like, we generate a lot of strings with a known amount of bits, and we encode them into the model by training for a really long time. And then it turns out, like, if you have a model that can give you a probability distribution, you can compress things better with the model. So, like, if the string was 1, 0, 1, 0, 1, 1, or whatever I said, if it's 6 bits and then you can compress it with the model to 2 bits, then you can say, okay, this model must store 4 bits about this input. And what we ended up doing was like training models under that framework, like generate a lot of random data, train the model for 10 million steps or something, and then add up the total storage. So like do that computation of how well can you compress the data? How big is the data? Okay, the model must be memorizing the difference. And then if you add it up, it turns out that like no matter what distribution you use, no matter how many samples there are in the distribution, no matter what the bit length of each individual example is, or how you encode them into tokens, you always get the same number. And so, like, we did this for GPT models, and it was like no matter what the size of the model is, the model will learn to store around 3.6 bits per parameter, which is kind of cool. That's like the upper bound, and I think that's in half precision, so like 16-bit float. The model's like, it's not super efficient, but it has to do a lot behind the scenes. So yeah, out of the 16 bits, it can use like a little less than 4 of them for raw storage.
Mm-hmm. Okay, cool. Let's go ahead and just move on to some of your papers that we think are really exciting. So, perhaps your most cited paper is TextAttack, which I think is something that you worked on during undergrad. Maybe just tell us a little bit about that.
Yeah, yeah. I think I touched on this a little before. Yeah, the way I've been explaining it now is like it really was a LLM jailbreaking framework before people use the word jailbreaking, but like maybe I'll tell you like the story. So I was getting into this area like why are the NLP models so bad? Why do they fail all the time? And I found out actually, let me step back one more step. There's this whole area of literature on adversarial examples for computer vision. Like you can make a small change to an input, and in the case of vision, where the images are differentiable, you can just like add this tiny, very very cleverly chosen amount of noise and like kind of change the classifier output. So a bunch of people tried to apply this like just with almost no thought, it felt like, to language models. Like they were trying to change a word or change a few words, and they had different, I don't know, rules for what counted as a valid change without changing the input too much. And basically, there were 20 or so papers that came out from probably 2016 to 2019 that were all doing this kind of like text adversarial example generation. And they were all really similar. Like, and so basically, we wrote software that included like only the small component that was unique to each paper. Or like it was like a system of components that you could kind of compose to build any of those papers and a lot of other stuff, if that makes sense.
Hmm.
It was really at its core like a framework to explain all the papers people were writing. I think our motivation was like, you don't need to write an entire paper to propose like a slightly different way of swapping words, but like people were doing that, and also like they weren't really comparing to each other in a fair way because they had like slightly different combinations of these modules. So we built them all. It was a pretty rigorous project of like, why is the why is the attack success rate 83.7? It should be 79.1. Like, is the model different? Is the process different? Is the way we're measuring similarity between texts different? Like a lot of kind of like very careful benchmarking, and we emailed with a lot of the authors of papers and stuff, but in the end we had this pretty useful Python package that you could do a lot of other stuff with, and I think people used it a lot. So I think the reason why it has so many citations is because it's just like, it's not necessarily because a lot of people are re-implementing those specific papers. It's more like the framework that we built is pretty useful to do a lot of new stuff. So people can like download it and use the models and just add one or two components and work on like new research.
Hmm. Yeah, that makes sense. And then I think you have another paper titled Nomic Embed, Training a Reproducible Long Context Text Embedder. I think we already talked about some of your work into contextual text embeddings, but you want to maybe tell us a little bit about this paper?
Yeah, yeah. This is a collaboration with some folks at Nomic, which is a startup in New York, especially led by this guy, Zach Nussbaum, who's the first author of that paper.
Hmm.
And they wanted to build as good of a text embedding model as possible with open data and actually open source all of the training code and all of the data they use. And so my input was more about like just making sure we were we were doing things in a way that was super reproducible and helping write the paper. Like Zach trained, I think, all the models. And that's a similar thing where it's like, one, useful for people to build new models because now they know actually what data to use and how long to train for. And two, I think the model itself is very useful for people. So it'll probably get a lot of attention from the community just from people that need good text embeddings.
Hmm. Awesome. And then there are a few other papers that you've worked on that might be worth touching upon. You have a paper on reevaluating adversarial examples in natural language that I think was also from undergrad. We talked a little bit
Right.
about inversion, which user like language model inversion paper. You have some papers on like extracting prompts by inverting LLM outputs. Any other papers that you think that you want to touch on?
Yeah, yeah. Go to the most recent one. Let's talk about that one. It's
For sure.
approximating language model training data from weights.
Yeah, from column 2025.
So that's one of those papers where I think it's a really cool new idea,
For
and
sure.
there will probably be a lot more work on this problem.
Hmm.
But the question is like, when you download a model, especially a really big model, and
Mm-hmm.
it's been fine tuned on some data, and you have the unfine tuned model. So, to give you a concrete example, DeepSeek R1
Mm-hmm.
is 405 billion parameters. No, I guess that's Llama 3, but it's like in the hundreds of billions of parameters. And we have both R1 and DeepSeek base. So, if you think of like the information theory perspective, we have a ton of bits. Like we have so many model parameters, and each one's, I'm pretty sure, at least 8 bits. And so that's like definitely a terabyte of data or more. And we have this difference in model space. So like if you were like a wizard who could sort of like traverse this high dimensional space and understand the relationship between different objects in the space, you could kind of look at DeepSeek base and look at DeepSeek R1 and see, wow, I have a terabyte of information about the difference here. Like I know they're doing RL, I know it's probably math. Like there's all this stuff you could probably learn from that weight difference.
Mm-hmm.
And so we kind of like formalized this problem and studied some toy settings of if you have the base model and the fine-tuned model, can you recover some approximation of the data that was used for fine-tuning?
Mm-hmm. Got.
And I noticed one thing that I thought was too bad was so OpenAI recently released this GPT OSS open source model,
Right.
but they only released the last checkpoint. So like there probably still is a lot of stuff you can learn from it. Like you can generate from the model and see that it's kind of like obsessed with reasoning and math and code, and you can look at like what words does it like and what's in the tokenizer, but we don't have the base model, so we can't do as much as we want. Unlike maybe Quen or something where we have like 2 model checkpoints, so we can exploit the difference and learn from it.
Mm-hmm. Okay, cool. And then, are there any other papers from like 2022, 2023, 2024 that you think are relevant?
That are relevant.
Yeah.
Um, yeah, I guess I can touch on one more thing, which
Sure.
is so I was talking about the embedding inversion problem.
Right.
That paper is called Text Embeddings Reveal Almost as Much as Text. And we were trying to recover the original text that goes into the output activation, which is used often for search, like in
Mm-hmm.
recommendation systems and in text retrieval. And we like this framework of looking at the output of a model and inferring what went into it. And so we were wondering if you could look at the probability distribution output of ChatGPT,
Mm-hmm.
if you could recover the text that went into it. And I think that's interesting because they usually change what you type in. Like they at least prepend this long prompt called a system prompt.
Yeah.
And they might make other changes like, I don't know, remove any toxic words or try to get rid of jailbreaking. Like we don't really know what the actual input to the model is.
Mm-hmm.
And so we studied, again, this inversion problem, but in the perspective of next token prediction language
Mm-hmm.
models. And so one cool part of it was you actually can get the full probability distribution from OpenAI, even though they don't give it to you. They support this thing called logit bias, which allows you to kind of like upweight or downweight certain tokens in the output. So like if you're really clever with how you choose the logit biases, you can do like a per token binary search to find the exact log prob for each token.
Mm-hmm.
And then once you have that, you can do inversion. And so we were studying like given this next token probability distribution, which in our case is a ton of numbers, can we figure out what prompt was used in the input to the model?
Mm-hmm. Okay, awesome. Maybe we can maybe switch now into some of the other things you've been involved in. So throughout Cornell, you were also have been very active on Twitter. Maybe just tell us a little bit about some of the blog posts or maybe some of your interesting things that you feel like you've done over the past few years that are maybe aside from research, but just focused on generally information theory, science of AI, but maybe not just papers, projects, or cool things that you've done that you posted about that have gotten a lot of attention.
Sure, yeah. There's a lot of little code snippets and libraries like I implemented BM25, which is this kind of 1970s era search method on GPU, which I thought was pretty neat. Um, I think this year I've been excited about trying to blog more.
Yeah.
Now I'm getting behind a little bit again, but I feel like there's a lack of educated opinions about what the next few years of AI will look like, or even what the companies like the big AI labs are working on now.
Mm-hmm.
So it's been nice to kind of speculate, hypothesize. I think one post that I made that probably got the most attention, like, I don't know, a bunch of kind of like famous people reaching out to me,
Sure.
um, was it's called "There's No New Ideas in AI, Only New Data Sets," and
Mm-hmm.
it's about how like if you really boil down the progress of the last 6 years or so, it really came whenever we changed the training algorithm, but then we changed the training data to
Mm-hmm.
kind of unlock a new avenue on which to scale. Like GPT-2 or GPT-1 pre-trained on the entire internet. No one
Mm-hmm.
had ever learned from all the text on the internet before.
Right.
Instruct GPT is really like a way to, or Chat GPT, it's a way to like use human feedback to make a base model into a chatbot.
Right.
It's not like a new algorithm per se. It's actually a very old algorithm, but the data source is new.
Mm-hmm.
And then most recently, O1, O3, the reasoning models are pretty similar. They're training language models using a data source that we were not using before.
Mm-hmm.
And so if you extrapolate from that, whatever the kind of next order of magnitude innovation will be in ChatGPT like models would probably come from a new data source. I don't know what it is.
Mm-hmm.
I speculated, I think, in the post that it might be YouTube. I think more recently I've become bullish on ideas of like web agents or
Mm-hmm.
computer tool use
Mm-hmm.
training. I don't know what it'll be, but it'll definitely be new data.
Mm-hmm. Yeah. I guess that's a pretty good segue into some of our sort of next category of topics, which is sort of like your thoughts about various different specific fields that are going on right now. So, I mean, there's been a lot of hypotheses here. There's a lot of talk, especially on Twitter, X, whatever you want to call it, about, RL environments, what does training for RL look like, RL as a service, for deployed engineers that are specifically working on RL. There's some new sort of startups that are coming up that are basically creating new RL environments or helping different companies train their data, so sort of like RL for enterprises. What's your sort of thought on that field as a whole?
Yeah, I think it's hard to say what is actually going to happen,
Mm-hmm.
but I think a lot of important and smart people think that RL is like the future for AI advancement.
Mm-hmm.
And unlike in the pre-training data setting, it's not really clear what the right data is for RL.
Mm-hmm.
And even if it is, like, it's hard to get. And so we're definitely moving from this era of like everyone trains on all the same data, which is all the good text you can mine from the web,
Mm-hmm.
to every company has their own proprietary RL environments and data sets that they fine tune on.
Mm-hmm.
Uh, I will say, I think like RL is just remarkably good. Like, one thing that I thought was incredibly impressive and noteworthy is that if you look at, I mentioned DeepSeek base, DeepSeek R1.
Mm-hmm.
If you look at DeepSeek R1, it it gets better at creative writing. Like, it only gets trained on math and code,
Right.
but it gets better at creative writing. And I think that's really compelling. Like, that says that there's something kind of profound happening in this reasoning process inside the LLM. And if you believe that, then the right way to take advantage of it is to try to scale reasoning as much as possible, which means we need more environments, we need faster simulation, we need diverse environments. Like, we don't really know exactly like what scale looks like, but everyone knows that we need it. So I think, yeah, there's a ton of companies popping up that are trying to offer this service. There's a lot of like smaller independent research labs trying to like aggregate RL environments. I think we'll have a clearer picture of like what actually works in a year or so. And right now it's kind of crazy.
Mm-hmm. Yeah, totally. Are there any other fields, I guess, like within just AI generally, that you're very, very confident are important. Like for instance, there's this new movement towards AI for science. Some of your work, for instance, like I think while you were at Meta, you were working on the paper on like the 3.6 bits thing with sort of like how GPT style language models might memorize 3.6 bits per param. Maybe tell us a little bit more about some areas that you're excited to work on in the near future.
Yeah, it's a great question. I think most recently I've been thinking a lot about reasoning, like what it means. Does it have to use RL? Could you do SFT? What's the difference between supervised fine tuning and reinforcement learning?
Mm-hmm.
And also, combined with that, this idea that like some people say RL, like people have this mental model that RL makes really tiny updates to the model. Like
Mm-hmm.
if you train the model for a long time, you kind of like inject all this information into it, and then when you do RL, you're kind of adjusting the model in a very subtle way. Like like that Shoggoth meme
Mm-hmm.
where it's like this kind of giant monster and the RL is just like the tiny little face
Mm-hmm.
on the giant monster, which is pre-training or something. And like, is that actually true? And like, can you show that? Can you measure the difference in some kind of bits per sample and show that RL is like kind of less information intensive, or is it just changing the parameters less? And finally, how does this relate to our kind of current methods for training models without updating them much, like
Mm-hmm.
low rank adaptation or prefix tuning or other methods for like making small changes to models?
Mm-hmm.
I'm curious how that kind of lines up with the RL theories.
Mm-hmm. Gotcha. All right, let's pivot into our last topic here, which is just generally advice. So, I mean, you sort of like we've sort of gone through in solid detail. Your path throughout undergrad, your AI residency at Google, and now you're nearing the end of your PhD at Cornell. Maybe tell us a little bit about some of the things that you've learned there. So, if you were going back to me in undergrad, what sort of advice would you have given yourself to maybe things to know about a PhD? Any sort of like thoughts on how to find good research directions that you learned that you think would be good for other people to hear?
Okay, I think I have two concrete pieces of advice. One is don't follow the hordes. This is maybe a little bit hypocritical because I'm talking about how much I care about reasoning right now.
Yeah.
But that's a little unusual. I think most of the stuff I've worked on is a little more like off the beaten path. I think like I have kind of a unique perspective by now. So like hopefully if I end up publishing something else, like it would be kind of like from a different angle, if that makes sense. But
Sure.
like I think like it's possible to read too many papers to the point where you get kind of it's hard for you to think of new ideas because you have so many of other people's ideas kind of in your head. And actually like it's almost better to just like kind of explore things on your own and work out things from first principles and then turn to papers like whenever you need. Like if you're running something like some algorithm and it's like incredibly slow, like why is it so slow? Like go into the code, like benchmark it. Like what's so slow? Is it an algorithmic issue or like kind of a systems issue? Like how can you fix it? I guess my point is like I think it's really important to think for yourself. And like, even if you're not working on the most, like, I will say there are a few people who like sort of systematically identify the most important things in AI and kind of like publish something in them. But that doesn't necessarily mean you're moving the field forward in a meaningful way. Like, I think the most rewarding research is like if you look back in 2 years and you didn't do it, then no one else would have done it. And I
Mm-hmm.
think like if you're working on something you think just because you want to get it out before someone else, that's not sustainable.
Mm-hmm.
Um, okay, my second piece of advice is that I think depth is a lot more valuable than breadth in the long run,
Mm-hmm.
like both in academia and industry. Like, if I were an undergrad, I wanted to get into I think most people's path would be like read the textbooks and watch all the videos and like expose yourself to as much information as possible, which is breadth. And breadth is good, but like what you really want is like depth because depth is what makes you unique, which is what makes you valuable. So like just as an example, someone asked me recently, "Oh, what should I do?" Like I want to kind of start working in AI and I was like I just sort of picked something specific and told them to go deep. So I said, "Oh, you should just download SGLang, like the inference framework and just look for some issues and start fixing them and work your way up to bigger issues. Because like there are only a handful of people in the world that know SGLang well enough to fix, like core issues with the framework.
Mm-hmm.
And like if you can do that, like you're already kind of a contributor to the forefront of AI.
Mm-hmm.
But like if you can do that, that doesn't mean you know a lot about RL or about multimodal models or about
Mm-hmm.
search or whatever. It just means you're good at SGLang. And I think that's like actually better, I think,
Mm-hmm.
than knowing a modest amount about many topics.
Mm-hmm. Yeah, I mean, I agree that depth is important. So in terms of people developing that depth and sort of trying to figure out like what specific area they should focus on, how do you think they should go about that? Like really figuring out like what they're really interested in at the beginning.
Yeah, that's a good question. Probably work on a few different things um, with fixed timelines, you know,
Mm-hmm.
like spend a few months working on SGLang, spend a few months building a new RL environment, spend a few months trying to write kernels for GPT OSS or whatever, and see like
Mm-hmm.
which do you think you have an advantage in, which do you find most compelling? Like what you know, everyone's different.
Mm-hmm. Yeah. Okay. Awesome. Well, thank you so much for your time. Really appreciate you coming on the podcast.
Thanks for having me.